Friends, we are discussing extraction of thorium. Let us retrace our steps a bit. I have told you that essentially to get thorium, we have to process beach sands. Now, sun-dried beach sands contain small amount of monazite, 0.5 to 5%, whole lot of ilmenite, garnet, zircon, silica and many other things. And after we have screened to remove lime shells and trashes, low intensity magnetic separator will remove ilmenite, which is highly magnetic. Then low intensity magnetic separator will recover monazite, sorry, the other way, the low intensity magnetic separator will remove ilmenite, which is highly paramagnetic, and then from the tailings high intensity magnetic separator removes monazite, which is weakly magnesite. Then the other constituents are removed by electrostatic separators, air tables and other things, etc., etc. The monazite in India, the concentrate is processed through the alkali leaching route. Here the peculiarity is, by leaching we do not take out thorium in the solution, rather we produce an insoluble cake which would have the thorium, easily soluble things that we do not want go into the solution, from which we will recover sodium hydroxide for recirculation. From in the cake, after acid leaching, we separate the thorium concentrate. I also mentioned that when you have thorium ions, uranium ions, rare earth ions in solution, then we separate them by adjusting the pH. And quite often at the same pH, more than one can precipitate. So, there can be a mixture of things. In the case of thorium, we can have high selectivity of thorium, provided we keep the pH value very low. So, there are ways and means of producing a pure thorium compound, and from that we get thorium oxide, or we can get an halide out of that. Now, we come back to the same question as we had for extraction of uranium from its compound. How do you proceed to convert the oxide or the halide into the metal? An obvious thing would be metallothermic reduction. Here are quite a few reactions and the free energy data for that. You know the guidelines. We will have to choose one that would have a negative free energy change. We will also like to have one which has high exothermicity, and then we have to worry about the state of the physical state of the reactants and products at the temperature of reaction. Now, I have given here also some data for carbon reduction of thorium, and as I keep on mentioning that for reactive metals like uranium, thorium, plutonium, titanium, in theory carbon reduction is always possible, because if you go back to Ellingham diagrams we had discussed, carbon forms carbon monoxide, which becomes increasingly stable as the temperature goes up, whereas all oxides becomes more and more unstable at temperature goes up. So, somewhere there is a temperature where carbon monoxide is more stable than the metal oxide. Now, for these stable oxides, very highly reactive metal oxides are very stable, but if you go to high enough temperature, carbon can certainly reduce. So, that carbon monoxide will form, taking out that oxygen from the oxide. But then the problem here is, here if you see the reaction thorium oxide plus carbon, the carbide formation also has minus, delta G is minus, means they form carbides. So, we cannot go for carbon reduction. Of course, we had the similar problem in ferroalloy production. So, we had subsequent methods of removing carbon. This is too complicated, it is not desirable to go for a to produce a carbide containing metal and then worry about carbon removal. So, we will not touch the carbon reaction at all. You find here again, here is the calcium reduction of thorium fluoride, which has a negative free energy change, means it is quite feasible as it is. Of course, in all cases we can make them more feasible if we can drive the reaction to the right by either dissolving the metal or dissolving the other thing into solution. So, that the activities are less, reaction moves to the right. We are looking at purely a pure compound, pure reductant, pure metal and pure salt being produced. So, it is quite obvious that calcium reduction is thermodynamically most attractive. You see thorium tetrachloride being reduced by calcium also has a negative free energy change. Now, we can help this reaction by introducing in the system some other salt to make a lower melting slag. For example, suppose you want to reduce TiO2 by calcium. The reaction is here, TiO2, calcium, thorium to CO, the free energy change is positive, means it looks thermodynamically not feasible. But suppose we introduce in this system some calcium chloride, so that the calcium oxide that is produced mixes with calcium chloride. In that case, the reaction would be feasible, because the activity of calcium oxide would be less, it can move to the right. So, such tricks we can try, provided calcium oxide and calcium chloride mix together, of course. Now, thorium oxide is often reduced by this reaction, and about an hour is allowed for the reaction to be completed. Then finally, thorium can be separated by leaching the slag with water and then with 1:10 nitric acid, followed by washing it with water, alcohol and then ether. The resulting metal powder is dried in vacuum and to give a purity of 99.7 to 99.8%. So, essentially we fall back on metallothermic reduction of a uranium compound, for a thorium compound, sorry. Now, we leave thorium there, we move to zirconium. I had mentioned earlier that zirconium is also a reactor metal, although it has nothing to do with nuclear reactions, but we call it a nuclear reactor metal because zirconium is vitally needed in the construction of nuclear reactors. You must understand why. Now, zirconium of course has many applications. The alloys are used, there are alloys where zirconium is used, but the most important property of zirconium that we want to exploit in nuclear reactors is low value absorption cross section of thermal neutrons. What does that mean? That means, when there is a nuclear reaction going on and neutrons are emitted, we do not want the neutrons to be absorbed and lost, because we want the neutrons to be available for carrying on more fission reaction. They should be available to go and impinge on another atom of a fissile atom, so that more neutrons are produced. Now, when we have this fissile material, they have to be contained somewhere. Zirconium is an ideal container material. The fissionable material is contained in zirconium alloy tubes. Firstly, because of low value absorption cross section of thermal neutrons, it allows the neutrons to pass through, it does not absorb the neutrons. Secondly, it also has good corrosion resistance and high temperature mechanical strength. So, all these make it an ideal material, of course not pure zirconium, some other things are mixed with it to form an alloy which will stand high temperatures, which will not be corroded, which will not be, which will stand all the radiations in the nuclear reactors, and most important, it will not absorb the neutrons, because they would allow the neutrons to pass from one place to another, one pile to another pile to carry on the fission reaction. Now, try to understand what happens in a nuclear reactor. In a nuclear reactor, when a given mass of fuel material is undergoing fission, fast moving neutrons generated face the following possibilities. They have been generated at one place by a fission reaction, then see what happens to these neutrons that have come out of the fission reaction. First, they may encounter another additional fissile mass producing more neutrons. This is what we want for the fission reaction to be carried on. Whatever neutrons that have been made available by fission reaction, we want they should encounter additional fissile mass and produce more neutrons, and this must go on. There is a second possibility that the neutrons that have come up encounter a fertile atom, not a fissionable material, a fertile atom, and produce another fissile atom. Like when you are starting, you cannot have pure uranium-235, you have an enriched material, uranium-235 as well as uranium-238. The neutrons, if they impinge on additional uranium-235, more neutrons will be produced. But instead of that, if the neutrons from a fission reaction impinge on uranium-238, then that uranium-238 gets converted to plutonium-239. So, the neutrons have achieved a useful function. It has not taken part into more fission reaction, but it has produced a fertile mass. Now, it is possible that these neutrons may encounter some other atom without any useful result. Means it goes and hits some other mass which is neither fissionable nor it is a fertile material. In case you are losing that neutron, it does not serve any purpose. There is a fourth possibility that the neutrons may escape altogether without serving useful purpose. It neither encounters a fissile mass to generate more neutrons, does not encounter a fertile material to produce a fissionable mass. It is not lost into something useful, some other material, but it simply escapes the system, it goes out of the system. Now, if the first thing predominates, means one predominates, then the fission is accelerated, because from one neutron you are producing two neutrons, they are producing some more neutrons, the heat generated is removed by a coolant. This generates a lot of heat, because every neutron, every fission reaction means generation of neutrons, thermal neutrons. Also, the fissile material is split into two equal masses which go in opposite directions with high energies, and this there is a lot of heat generated by that process. The material in a cladding material like zirconium alloy stands that heat, but at the same time we have to take out that heat, because that is the energy which you are going to use from a nuclear reactor. So, that is removed by a coolant. a liquid will flow all around those tubes which contain where a nuclear fission reaction is taking place. That liquid will come out with all the energy, heated form, from which energy will be taken out. This could be heavy water, it could be other things. The cladding element, which is made of zirconium alloy, must not absorb neutrons, because if it absorbs neutron, it goes against the fission reactions. So, it must not absorb neutrons. What about this possibility that some neutrons may escape altogether? Means there are a lot of tubes, cladding elements where fission reaction is taking place, coolant is flowing between them. Now, what happens if some neutrons escape altogether? We have to eliminate that possibility. To do that, there are some moderator rods that are inserted now and then. Their function is to slow down neutrons. Some neutrons which are moving so fast that it may escape the system, they are not allowed to escape the system, they are slowed down, so that they eventually go and hit another fertile mass, or they go and hit a fissionable mass. They are not allowed to escape altogether, they are slowed down by using moderator, and beryllium has that function. It can slow down the thermal neutrons, and that is why it is also a nuclear material. Now, you never have a mass which is all fissile material. No, that is not possible. You can enrich a mixture of uranium 235 and 238, so that there is more uranium 235. It becomes a mixture of fissile and non-fissile atoms. Uranium 238 is not fissile. From there we will produce small amounts of plutonium 239 that will be fissionable, provided you can extract it and get a good amount of it at one place. But for a given mixture of fissile and non-fissile atoms, there is a certain critical size beyond which the proportion of neutrons that escape is so reduced that the condition for a nuclear reaction to take place is attained. You must understand that what makes a nuclear reaction possible. A nuclear reaction is possible when you are generating more and more neutrons very rapidly in an accelerated fashion, and that will be ensured by non-escape of neutrons out of the system. Whatever is being generated must be used to go and hit another fissile mass, so that more neutrons are created, and there is a certain critical size. If the size is too small, then no matter what you try, the thermal neutrons just do not have enough of mass around to get all absorbed, it will escape the system. So, there has to be a critical mass for a given mixture of fissile and non-fissile material. In that mass, it will now be possible to ensure that the neutrons do not escape altogether, that it will take part in fission reactions, and there will be a nuclear reaction. So, zirconium alloys which have low capacity of absorbing neutrons allow the pile to be kept as small as possible, because if the zirconium alloys were not there, then the piles cannot be that small. Now, how do we produce pure zirconium oxide? It has to come from zircon sand. Again, here the technique is slightly different. We do not leach zircon sand by an alkali. This is a classical chemistry method that you fuse zircon sand with caustic soda, and after we got a mass, solid mass, that will be leached. So, there is a solid state reaction followed by leaching, and then of course, we decant waste, there will be slurry filtration, there will be a cake which is basically a zirconium hydroxide that will go through some other steps like tributyl phosphate solvent extraction method, some scrubbing, finally zirconium stripping solution, then ammonia will finally precipitate a zirconium hydroxide which will be dried to get zirconium hydroxide that will be calcined to produce pure grade zirconium oxide. So, we are starting with zircon sand made an alkali fusion with alkali, a cake that goes through some reactions and finally a solvent extraction process. So, that finally you produce nuclear grade zirconium oxide. So, these are standard steps, and once you got pure zirconia, we can produce from that zirconium sponge metal. It is called zirconium sponge because it will have lot of holes like your sponge have, and finally, it has to be consolidated. How do we produce this sponge? It is very simple. It will with carbon binder, there will be wet extrusion, drying, coking, coked briquettes. So, essentially we are reducing by carbon zirconia ZrO2 plus carbon, it will now be chlorinated. So, it is chlorinated in presence of carbon. So, zirconium oxide I have mentioned, it is too stable an oxide, without carbon it cannot be chlorinated. In presence of carbon it will be chlorinated. We will find this carbon is coming from recirculation. We produce zirconium tetrachloride gas, it will be reduced by magnesium in the gas phase. And then finally, we will produce zirconium which will go for vacuum distillation to get rid of the excess magnesium that we have used in the reduction process. We get a raw sponge, it will be crushed, screened, then blending, nuclear grade zirconium will come, and from all this off grade sponge will be recirculated for chlorination. So, again here we are following a chlorination route, but from the chloride we are going for again metallothermic reduction by magnesium. It is done in gas phase, zirconium tetrachloride gas being reacted with magnesium gas. It has to be obviously done in a closed reactor. Sometimes we produce zirconium powder. I will go through the steps just to, I do not think there is anything that needs any special mention. Zirconium is sometimes required in the powdered form for non-nuclear uses. This powder is produced by calcium reduction of the oxide. For nuclear grade, we went for magnesium reduction. Now, we are going for calcium reduction. In a finely ground zirconia, after dehydration, powder reduction will be done by calcium metal in presence of calcium chloride, the same technique. So, it is a calciothermic reduction in presence of calcium chloride. The calcium chloride is simply to produce a lower melting slag. So, it is to drive the reaction to the right. And then the powder reduction will take place around 950 degrees in argon gas. We have a cooled reduced mass leaching slurry, again leaching by hydrochloric acid. We get a metal powder slurry because you already have the zirconium in the reduced mass. The hydrochloric acid solution is simply taking away all the muck, leaving the metal powder, and then deionized water, final washing, air drying zirconium metal powder. So, all these are examples of metallothermic reduction. here, sometimes by magnesium in gas phase, sometimes by calcium in gas phase. We are adding calcium chloride to drive the reaction to the right. It's very simple principles of how you manipulate the free energy change for the reaction. If there is not enough heat, you have to supply heat, otherwise things can move on their own. Now, we will come to production of beryllium. Now, beryl, I have beryl is a, let me tell you what beryl, this is beryl 3BO Al2O3 6 SiO2. Beryl is a very interesting mineral, and sometimes hexagonal crystals of this beryl are also found in the mines. But then we are not talking about that now. We are just trying to say beryl as we find in mines. This beryl crystals can be picked up. Actually, beryl is a very hard substance, the mineral, and the way it is processed is very interesting. Beryl is heated to a high temperature and then the whole thing is put into water, so that there are quench cracks. Otherwise, it is very hard to crush and grind beryl, and but by this heating and quenching you create internal cracks, then it becomes very easy to bring down the size. So, that is what is done, and after melting in electric furnace, then quenching, kiln treatment, we do grinding, leaching and all that in sulfuric acid, then ammonia treatment, you remove iron and beryllium is precipitated, finally beryllium hydroxide. So, these are chemical steps, you have to produce beryllium oxide. Then there is a very interesting situation here. In the case of beryllium, we need not go through the halide route, and very often beryllium can be reduced by carbon in presence of copper to produce copper beryllium alloy. Now, try to understand why we do that. Firstly, if we have copper in the system and we are producing beryllium as an alloy, then this reaction is driven to the right, because the activity of beryllium becomes less than 1, and if it becomes less than 1, then it may not form beryllium carbide also, in case there was a possibility. There is another advantage. In the industry, beryllium, copper beryllium alloys are needed. Actually, a lot of beryllium is used as copper beryllium, as springs. Copper beryllium alloys make beautiful springs, which retain their springiness. So, it is double advantage. You are getting a product you want, at the same time the product makes it easy for the process to occur. So, beryllium oxide is reduced by copper, reduced by carbon in presence of copper. We produce copper beryllium alloy and CO. So, now by maintaining a low concentration of beryllium, carbide formation is avoided and the reaction is made easier. Now, we have to ensure that the beryllium concentration alloy is not high. Then again you get into the question of forming beryllium carbide. But it is a beautiful example of manipulating a reaction to get the product you want and avoid getting a product you do not want. Normally, if you take beryllium oxide, you reduce by carbon. According to Ellingham's diagrams, there is a temperature beyond which carbon monoxide will be more stable. You can refer to the diagram and get the temperature, but the product would be not pure beryllium, but beryllium and lot of beryllium carbide as well. How do we avoid the carbide formation? By not producing pure beryllium. We produce copper beryllium alloy and also ensure that the beryllium concentration is low. So, the beryllium carbon reaction will not take place. Now, fortunately, this alloy that we are producing itself is of use in the industry. So, we are killing couple of birds with one stone. Bring in copper, make the reaction feasible at a lower temperature, 1. Bring in copper, reduce the activity of beryllium, reduce quite a bit by making it a dilute solution of beryllium in copper, then beryllium carbide does not form. Also by carbon reduction in presence of copper, produce an alloy which you need in the industry. So, you have done 3 things by 1, which is a beautiful example. Now, of course, this is when you want to produce copper beryllium alloy. Now, you might like to produce pure copper, pure beryllium. In that, this process will not work, because you cannot pure beryllium you cannot produce by carbon reduction. So, we want to go again to the halide route. Pure beryllium must be produced mainly from halides. In this context, magnesium reduction of beryllium difluoride has been successfully employed. The reaction is BeF2 plus Mg Pe plus MgF2. So, you see, for all these cases, uranium, plutonium, thorium, beryllium, we have always aimed at producing a pure oxide, then try to reduce the oxide metallothermically or convert the oxide into an halide and try to reduce metallothermically. Question is, can we use an electrolytic method? Now, I should tell you once again that very rarely can an oxide be dissolved in a halide. Only exception is Al2O3 dissolving in a molten salt like cryolite. There are few other examples of an oxide dissolving in a salt, but oxides dissolve in other oxides, and generally it will be, if these are acid oxides, stable, they will be in basic they are basic oxide, they will go into acid oxide like silicates, phosphates, aluminates. Now, they are highly viscous. You can't think of using them for electrolysis, but fluorides and halides certainly you can. You can, if you can make uranium halide, plutonium halide, thorium halide or beryllium halide, you can produce the metal electrolytically. But then the question is, what is easier to do? In many cases, metallothermic reduction is easier, and that is why metallothermic reduction is what we do. Now, I move to a metal which is of vital importance, which is titanium. India actually should be a country that should produce a lot of titanium metal, because we are rich in ilmenite deposits. Unfortunately, we have so far produced only pure TiO2 from ilmenite. That ilmenite is FeO-TiO2, and from that we remove that FeO part, produced TiO2, which is rutile. We call it artificial rutile when we produce from ilmenite. It goes into the paint industry, because TiO2 is absolutely white. So, this makes the basis for paint making, but from TiO2 to Ti is not an easy step. So, although we know it, a pilot plant has been run for a long time in Hyderabad, DMRL Hyderabad, and I will talk about that. We still have not been able to have in India a commercial process for production of titanium. Why do we need titanium? Titanium is known for a very high strength to weight ratio. It is nearly double that of steel. means we can get the same strength as steel using only half the weight of titanium. So, titanium aluminum alloys have now become irreplaceable when we come to making of aircrafts or aerospace, where we need lighter weights, but strength. It has some other advantages. Its corrosion resistance is better than that of 18H stainless steel. So, on one hand, you have a material which is strong, and in comparison to steel, for the same kind of strength, its weight is half. Then it is also a highly corrosion resistant, as better than 18H stainless steel. There is another advantage. It retains, the titanium alloys retain strength even at high temperatures and show less creep, which not many steels can do. Steels may have the strength, it may have the corrosion resistance, but it will have more weight, and it will be very difficult to have high temperature resistance to creep. And you know what is creep? Creep is under a load, a material slowly deforms. So, titanium alloys even under load at high temperatures will resist deformation, there will be no creep. And that is why it finds now applications in jet engine components. 45% of titanium is going into jet engine components, in airframes, in missiles and spacecraft 20%. That is the relative consumption of titanium. It does not mean 20% of spacecraft is made of titanium and aluminum alloys. No, it shows is total consumption of titanium is 45% in jet components, airframes 25%, missiles and spacecraft, but it is there everywhere. You cannot think of an applications in aerospace without titanium aluminum alloys. So, we need to produce titanium in our country. So, you need to know a little bit about how titanium can be produced. Now, ilmenite is FeOTiO2. This is the ore mineral of titanium. There is also rutile, which is pure TiO2. I mean, mineral is pure TiO2. But ilmenite is usually far more common than rutile. But wherever you find ilmenite or rutile, you are not going to get a necessarily very high grade of that mineral. As I said, in the case of beach sands, for example, 45–50% was ilmenite, then there were a whole lot of other things. But still that ilmenite was far more than monazite or other things. So, ilmenite is not that rare a mineral. Plus, you have seen that it is highly magnetic. So, it can be separated out by low intensity magnetic separators. So, there it is very quite easy in the industry to produce ilmenite concentrates. It is not difficult at all. Now, for artificial rutile or production of TiO2, they have to reduce the FeO part, and it is not very difficult. Even at moderate temperatures under reducing conditions, TiO2 will not be reduced. If FeO part will get reduced to iron, that iron is leached out. There are several processes of leaching. Actually, it is a kind of process of corrosion, like iron is corroded. So, similarly, some oxidizing medium iron will be taken out as iron hydroxide, and it will be removed, it will be left out with TiO2, which will go for paint industry. Now, as I said here, the ilmenite ores can be magnetically concentrated to produce almost pure mineral, 90 to 95% ilmenite. The leftovers yield valuable raw materials. Always ilmenite is associated with lots of other valuable minerals, and for the extraction of zirconium, thorium, rare earths, etc., they will all come from the rest of it. And so, the beneficiation procedure for beach sands we have discussed several times. I have a mention of processing of beach sands, which give us ilmenite, monazite, garnet, then other rare earths, etc. Now, Indian ilmenites, I am giving the approximate analysis of two ilmenite containing beach sands. Analysis of ilmenite. There is one in Chavara, there you see 60% TiO2, then there is Fe2O3, FeO, and then whole lot of other things, including rare earth traces. Then there is another one, Manavala Kuruchi, I think it is in Kerala. You have TiO2, then you have Fe2O3, you have FeO. So, in different parts of India, there are beach sands which all contain ilmenite, but with different kinds of impurities. So, their treatment procedures are not all identical. Now, here is something I have written for treatment of ilmenite for upgradation. Let me read that. To obtain titanium from ilmenite, the ore must be upgraded to a titania rich product containing over 90% TiO2. So, first again we have to try to produce an intermediate concentrate which is very rich in TiO2, and we are saying 90% TiO2. The upgraded ilmenite is known as synthetic rutile. As I said, rutile is pure TiO2, this is called synthetic rutile. Now, apart from being the desired raw materials for indigenous titanium production, this upgraded concentrate is used for pigment grade TiO2 production and has a good export market. That TiO2 we have done some value addition. From ilmenite, if we have produced synthetic rutile, we have made some value addition, because synthetic rutile TiO2 will fetch much more value than ilmenite as such. It has an export market. But if you can reduce TiO2 to titanium, then you can add far more value. This at this moment we are not able to do, but sooner or later India will have to do this. Now, ilmenite contains titanium and iron oxides, as I have shown in bound form. You cannot say ilmenite is a mixture of FeO and TiO2. It is a compound, FeO TiO2 in bound form. We call it a spinel, and therefore, it cannot be upgraded by physical methods. You cannot physically remove FeO and TiO2, you have to go for a chemical processing. Most beneficiation methods aim at removal of iron oxides by preferential chemical reaction with suitable reagents, as I mentioned. The methods used are as follows: the reduction smelting of ilmenite with carbon and a suitable flux, resulting in a titania rich slag and pig iron. Now, there are three basic methods which I have listed here for removing FeO and TiO2, or rather the iron value and the titanium value. Now, in our industries today, what we are doing is, because we are mostly interested in producing synthetic TiO2, we reduce the FeO part to iron, then we rust it. The process is called rusting of that iron to produce an oxide, and then TiO2 is separated from what is now discarded. So, if you go to Indian rare earths in Chhatarpur, which is near Bhubaneswar, they are producing synthetic rutile. There are dumps of rejects which contain 50% iron. So, it is almost a raw material for iron production for some other countries, not for our countries. In our country, we have rich iron ores and they do not know what to do with it. These are one of the big environmental issues in non-ferrous metal industry. I mentioned one about red mud, that in when you are trying to produce aluminum from Al2O3, bauxite is leached by sodium hydroxide, so that aluminum is taken into solution as sodium aluminate. The insolubles called red mud are simply disposed and kept aside in big places which occupy a whole lot of places. This red mud has iron oxide, some TiO2, some vanadium, other things. It has a lot of iron oxide, 40% or so iron. Similarly, we have also here an environmental issue. If we are simply going for TiO2 production, we are not interested in the FeO part. We reduce first, so that to break the chemical bonding between FeO and TiO2, iron comes out. Then that iron that has come out, we rust it, means we oxidize it by various oxidizing agent, make iron hydroxide, and from that is thrown out. We are losing that iron value for a moment. So, there is a process where they say no, let us not do that, let us reduce FeO-TiO2 the whole thing by carbon using a suitable flux. So, produce pig iron like iron smelting. Your goal is to produce pig iron and there would be a slag which will be rich in TiO2. So, we go for a pyrometallurgical process of reduction by carbon of FeO-TiO2 using a flux which will produce a slag. Like flux means you have to put quartz, you have to put limestone. The product will be pig iron and TiO2 go into the slag phase. So, the pig iron will fetch value, and now titanium will have to be extracted from that titaniferous slag. So, now we have gone from ilmenite, where titanium was bound with FeO, to titanium in a slag phase. But the advantage there is we have produced pig iron in the process, which will have a market. From that slag, we will have to take out titanium, which can be done by halogenation. We can halogenate we can chlorinate that slag, get a titanium tetrachloride out of that, or some other process you can think of. So, that is number one way of handling ilmenite to get titanium. Then there can be direct leaching of ilmenite with acids under atmospheric pressure or high pressure, resulting in preferential dissolution of iron. This has also been tried. To remove iron, first we thought reduce, take out iron, oxidize, separate, but there are also processes where the ilmenite is directly leached, and acids are very strong reagents. Preferentially they will dissolve the iron part, leaving aside the titanium part. Then it is also possible to directly go for selective halogenation on the ilmenite, so that iron oxide will produce volatile iron halides under certain temperature, leaving TiO2 behind. So, there are different approaches of separating iron from TiO2. Eventually, we need to produce TiO2 or a halide of titanium, from which we will produce the metal. Now, here is what we have mentioned, what I just now mentioned, I have put in a flow sheet form. we produce an ilmenite concentrate, then we have the following choices. We go for smelting in an electric furnace, which will produce pig iron, and we produce high titania slag, just like an electric furnace operation. We can go for acid leaching. This high titania slag can also go for acid leaching. Instead of the ilmenite concentrate being done, we can do this, take out the pig iron part as pig iron, then the slag itself is leached, so that we can produce a high iron waste. Here this iron is being wasted. If we go from the slag to acid leaching, we are only wasting the iron that has entered the slag phase, but we have taken out most of the iron here as pig iron. But if you go for direct acid leaching, we will produce a high iron waste, and then we will have TiO2, which will go for chlorination to produce TiCl4. Or we can go straight for chlorination of the ilmenite concentrate. That would also produce a high iron waste, that will go to waste, unfortunately. But it will leave behind TiO2, which can be chlorinated to produce crude TiCl4. It will be refined by vacuum distillation. This will also be vacuum distillation, so TiCl4. So, these are the three steps. The advantage here is you produce iron as a valuable product as pig iron. In these steps, we are actually rejecting iron as a waste, and it is very difficult at this moment to do something about it. That is why you find in Indian rare earths dumps of waste, iron rich waste, which have come out of that ilmenite. So far, no use for it. It also has other things, it has other valuables also in that. But eventually, here also we are going for production of an halide. Now, it should be noted that the presence of excess carbon produces pig iron. Here, we need a lot of excess carbon to produce pig iron. The slag contains 70 to 80% TiO2, it will be very viscous slag, 5 to 10% iron, which we are going to lose here. There will be oxides of Mg and CO from gangue present in ilmenite. If the ore contains oxides of metals such as chromium and vanadium, which are very often present, then these oxides are also reduced to a large extent. And if they are reduced, they will enter the pig iron thing. Pig iron will contain that chromium. If not reduced, vanadium may not be reduced, it will go into the slag phase. The pre-reduction of ilmenite often helps the smelting production. Pre-reduction means if we initially reduced ilmenite, as I had mentioned, into Fe and TiO2, then go for smelting. Sometimes smelting becomes easier because you have already taken out iron from the FeO part. The electrothermic smelting process has found commercial applications in many countries: Canada, USA, Norway, Japan and USSR. Actually, it is Canada which first introduced method that makes better use of the metallic value. You take out iron also, you take out titanium, and you are not to worry about generating lot of waste, because in this case you are not generating that iron waste which these routes are generating. Now, in the next lecture I will come to chlorination of TiO2. It is a very interesting step, and because we are talking about chlorination so often in the past, maybe if I talk about the chlorination of one oxide, I would be able to show the example of chlorination of all such similar oxides. So, I will continue with chlorination of TiO2 in the next lecture. Thank you very much.